Hello friends, welcome again to my channel, and today in this session we will discuss concrete mix design for pavements as given in IRC 44 2017. The objective of designing a concrete mix is to arrive at the most economical and practical combinations and proportions of different ingredients to produce concrete that will meet the performance requirements under specified conditions of use. So different ingredients in the concrete are cement, coarse aggregate, fine aggregate, water and admixtures. Now I would discuss these admixtures little later. As far as cement is concerned, it can be either ordinary Portland cement of 43 grade or 53 grade, but that is to be specified in the design. It can be pozzolana cement as per IS 1489. It can also be PSC, that is Portland slag cement, or it can be composite cement. IRC also permits use of mineral admixtures like fly ash, silica fume and other such materials, and they can be part of cement. When these admixtures are used, then in that case it is treated as cementitious material. So cement plus mineral admixtures, that is called the cementitious materials. Admixtures in concrete. There are two types of admixtures. One is mineral admixtures, other is chemical admixture. Mineral admixtures, as I told you, it can be in the form of fly ash, silica fume, or granulated blast furnace slag. And chemical admixtures are used for getting the desired property of the mix. And these chemical admixtures can be retarders in the form of plasticizer or superplasticizers. Retarders are admixtures that slow down the setting time of concrete, giving more time for placing and finishing the concrete. They are useful in hot weather or when concrete is to be transported over long distances. The plasticizers are used to reduce the amount of water in concrete mix, and superplasticizers are used to increase the workability of concrete without increasing the water content. These retarders can be used up to 0.5%, plasticizers up to 1%, and superplasticizers up to 2% by weight of cementitious materials. However, the dose of polycarboxylate based admixtures will not exceed 1%. A higher percentage of these admixtures may be used if agreed upon by the manufacturer and the contractor based on performance tests related to workability, setting time, and early edge strength as stipulated in IS 456. The second is the air entraining admixture. In freezing weather, use of these admixtures is recommended to counter the freezing and thawing effect, and they are also used for improving the cohesiveness of the mix and to reduce the bleeding. The total quantity of air in air entrained concrete as a percentage of volume of the concrete as defined in IRC 44 is like this. For a maximum size of aggregate of 31.5 millimeter, it can be 4.5 plus minus 1.5%, means 3% to 6%. And for 19 millimeter maximum size of aggregate, the air entrained may be 5 plus minus 1.5%. Now coarse aggregate. Coarse aggregate will be clean, hard, strong, dense, non-porous and durable pieces of crushed stone or gravel. These aggregates are to be tested for their suitability before using in the concrete, and for that these tests are prescribed in IRC 44. Combined flexibility and elongation index should be less than 35%. Impact value should not be more than 30%. Water absorption should not be more than 2%, but in some cases it can be allowed up to 3% when good quality aggregates are not available and other engineering properties are satisfied as per IS 383. The maximum size of coarse aggregate shall not exceed 31.5 in pavement quality concrete. The coarse aggregates are supplied in nominal size, and this table can be used as a guidance for procurement of coarse aggregate. For the maximum size of aggregate 31.5, 19 millimeter, 12.5 millimeter and 9.5 millimeter, these are the percentages as prescribed in IRC 44. Fine aggregate shall be free from soft particles, clay, shale, cemented particles or mica. Water absorption should be less than 3%, and as far as possible, the material passing 75 micron should be limited to not more than 3% when natural sand is used, not more than 12% when crushed stone is used, and not more than 8% when mixture of sand and stone dust is used. The gradation of fine aggregate should satisfy the grading zone as specified here, zone 1, zone 2, zone 3, and these are the sieve sizes and these are the ranges of the percent passing. Now zone here does not depict any location or region. These are the gradation of fine aggregate in a descending order of their sizes. Now in case of crushed stone sands, this limit at 150 micron can be increased up to 20%. Coarse aggregate and fine aggregate should be mixed in a suitable proportion to get the final grading as given in this table. Depending upon the nominal size of aggregate, for 31.5 millimeter, this is to be used. For 26.5 millimeter, this gradation is to be used, and for 19 millimeter nominal size, this gradation is to be used. 0 to 5% here is for crushed sand, and 0 to 2% here is natural sand. As I told you earlier, IRC permits use of mineral admixtures as part replacement of cement in pavement quality concrete, and one such admixture is fly ash, that is pozzolana. Fly ash conforming to grade 1 of IS 3812 may be used as part replacement of Portland cement. Maximum dosage as specified is 25% by mass of cementitious material. Similarly, silica fume, usually used in proportion of 5 to 10% of the cementitious material content of the mix. Use of silica fume is generally advantageous for higher grade of concrete, that is M50 and above. Metakaolin conforming to IS 16354 may be used up to 20% of the cementitious materials. And similarly, granulated blast furnace slag can be used up to 50% by weight of cementitious material at site with ordinary Portland cement of 43 or 53 grade. So these are mineral admixtures which can replace cement in the concrete. So when you design a mix, the basic data which are required for design of mix are given here. You need the grade resignation, that is the required strength, type of cement to be used, maximum nominal size of aggregate, minimum cement or cementitious material content, and maximum water cement or cementitious material ratio to be adopted, maximum cement content, workability required, that is the slump value, degree of site control generally taken as good or a value established through standard deviation, type of coarse aggregate and fine aggregate, admixture to be used, and mineral admixture to be used. So these are the data generally required for design of a mix. Now to explain the procedure of design, I'll take one example to solve here. An example is like this. Let us say we have to design a concrete mix for a flexural strength of 4.5 Newton per millimeter square. Type of cement is OPC 43 grade, maximum nominal size of aggregate 31.5 millimeter, and minimum cement content as per IRC 15 is 360 kg per meter cube, and maximum cement content is 450 kg per meter cube. So cement content is to be between 360 and 450. Maximum water cement ratio should be limited to 0.4. Workability is desired as 25 plus minus 10 millimeter. Degree of supervision will be good. Type of aggregate, crushed angular aggregate, and chemical admixture type is super plasticizer. So The first step here would be to conduct test on aggregate and fine aggregate to find out their suitability for use in mixed design. And the test which I told you are impact value test, shape test, water absorption test, all those tests are to be conducted. In addition to that, you need the specific gravity of cement, coarse aggregate, fine aggregate, and also the water absorption of coarse aggregate and fine aggregate to design the mix. The grain size distribution of coarse aggregate, let us assume that three fractions are available at site, and fraction 1, fraction 2, fraction 3. Fraction 1 is from 31.5 to 19 millimeter, fraction 2 is 19 to 9.5, and then down. These are the aggregates which are available at site in the form of coarse aggregate. You have to mix them in some proportion to get the desired grading. Fine aggregate, grading zone 2 as per IS 383, and once you know these basic parameters, then the first step is to determine the design flexural strength for mixed proportioning. IRC 44 suggests two equations. Now design strength criteria is that not more than 5% of test results should fall below the characteristic strength. Therefore, design strength should be higher than the characteristic strength given by these equations. FCR star is FCR plus 1.65 times standard deviation, or it is FCR plus 0.55. Whichever is higher, you have to take the design flexural strength. Now similar equation is given for the cube strength also. If the design is based on compressive strength, then similar equation will be that this will be, in that case it will be compressive strength, that is characteristic strength 28 days compressive strength plus 1.6 times the standard deviation. And the second equation is that this is cube strength plus a factor x, and x depends upon the grade of concrete. For M30 and M35 this value is 5, for M40 and M60 it is 6.5, and for M65 and above this value is 8. Now here in this example we are designing the mix based on the flexural strength, and therefore we will use these equations. This value of S is the standard deviation of flexural strength, and its value can be taken from this table. When you have the grade of concrete, that is characteristic strength 4.5 in our case, so its value is 0.4. So with this value you calculate what is the required or target strength, that is 4.5 plus 1.65 into 0.4, 5.16, or 4.5 plus 0.55, that is 5.05. So we will take 5.16 as the target mean flexural strength, 5.16 Newton per millimeter square. Now air entrapped. Selection of mixed proportions will require the estimation of air entrapped in the concrete. And IRC 44 suggests these guidelines that for nominal maximum size of aggregate, what should be the entrapped air? So for 31.5 millimeter nominal size, it is 0.8%, and therefore we take 0.8% as the air entrapped. Then comes the water cement ratio. Truly speaking, water cement ratio depends upon type of cementitious material, maximum size of aggregate, type of aggregate, grading of aggregate, and many other such factors. And therefore, it is always desired that a relationship be established between strength and free water cement ratio for the material to be used. Now, this table, which is given in IRC code, can be used as a guide to start the design. When you have the flexural strength at 28 days, 5 Newton per millimeter square, and for OPC 43 grade 0.34, for 5.5 it is 0.28, and therefore for 5.16 you can interpolate these values, and that is 0.32 for OPC 43 grade. Now similar table is given for compressive strength also. When you design the mix based on compressive strength rather than flexural strength, a similar table is given in the code. The maximum water cement ratio should be restricted to 0.4 when OPC is used, and since our value is 0.32, so we will use approximate water cement ratio as 0.32. The next is selection of water content. Water content also depends upon several factors, but the most important is type of cementitious material and aggregate size. This table is suggested in IRC 44 that for nominal maximum size of 31.5 mm, the suggestive water content can be taken as 165 kg per meter cube. So 165 kg per meter cube is the water content. Now this water content is for angular coarse aggregate and for 50 mm slump, and it can be adjusted after trials. Now in our case, the aggregates are angular, that is given in the question, but slump is 25 mm, and therefore this should be adjusted. Now for the workability of 25 mm, this water content which you estimated should be reduced at 3% for every 25 mm slump, plus for additional 25 mm minus for reducing the slump, and therefore the water content would be 165 minus 0.03 into 165, that is 160 kg per meter cube. Now water reducing admixtures are also being used here in this case, that is superplasticizer. Superplasticizer can reduce the water content or water requirement by 20%. Therefore, the actual water to be used will be 80% of this, that is 128 kg per meter cube. Then comes the calculation of cement content. We know water cement ratio 0.32, water content is obtained 128 kg per meter cube, and therefore cement content would be 400 kg per meter cube. And this should be checked for minimum and maximum value of cement content. This value of 400 lies between this range, and therefore it is correct. We can go with that. Then comes the sixth step, proportioning of coarse aggregate and fine aggregate. Now this is the zone 2 of our fine aggregate, and volume of coarse aggregate per unit volume of total aggregate for different zones of fine aggregate as suggested IS 383 is 0.65, that is for 31.5 mm nominal size of coarse aggregate, this ratio should be 0.65. And what it further says that proportion of volume of coarse aggregate is increased at the rate of 0.01 meter cube for every decrease in water cement ratio by 0.05 and decrease at the rate of 0.01 meter cube for every increase in water cement ratio by 0.05. That means this volume or proportion of coarse aggregate depends upon the V by W by C ratio also, water cement ratio. Now in our case, the water cement ratio is 0.32, and therefore the actual proportion of coarse aggregate would be 0.65 into interpolation of between 0.5 and 0.32, and that is 0.686, and remaining will be the volume of fine aggregate 1 minus 0.686, that is 0.314 per unit volume of total aggregate. Once you know the proportion of coarse aggregate and fine aggregate, it will be checked for combined grading to ensure that overall grading falls within the limit as given in this table. Now if not, then suitable adjustment in volume of coarse aggregate and fine aggregate should be made, but the final gradation should lie within this range. Once the grading is satisfied, the next step is to make some calculation for the mix. Absolute volume of concrete is 1 minus volume of air and content, and that is 0.8%, and therefore the volume of concrete would be 0.992 meter cube. For this volume, you can find out what will be the volume of cement, that is 400 kg per meter cube divided by its specific gravity, that is 0.127 meter cube. Volume of water is 128 kg, you can say 0.128 meter cube, and superplasticizer will be 1% by mass of cement, and therefore its volume will be mass of admixture upon specific gravity of admixture into 1 by 1000. So for 400 kg, 1% is 4 kg divided by its specific gravity 1.2, let us say, that comes 0.0033 meter cube. Then comes the volume of aggregate. Volume of aggregate would be volume of concrete minus volume of cement plus water plus admixture. That is 0.7337 meter cube. And the mass of coarse aggregate will be this volume multiplied by volume of coarse aggregate into specific gravity of coarse aggregate. So that is 0.7337 is the volume of total aggregate. Out of it, 0.686 the coarse aggregate, specific gravity is 2.74, and that comes 1379 kg per meter cube. And similarly, the fine aggregate would be 0.7337 into 0.314 into its specific gravity, and that is 604 kg per meter cube. Now we got the mixed proportion for trial 1. But this is based on aggregates in their SSD condition. SSD means saturated surface dry condition. Cement is 400 kg, water 128 kg, coarse aggregate 1379, fine aggregate 604, chemical admixture 4 kg, and water cement ratio 0.3. We are now ready to make the first trial. But when you make the trial, we should determine these weights of coarse aggregate, fine aggregate in their dry condition. For trial 1, based on dry aggregate condition, cement is 400 kg per meter cube, no change. But fine aggregate will now be 604 divided by water absorption, 1 plus 1%. That is 598. 598 will be the dry aggregate, 604 will be the aggregate in SSD condition. Similarly, coarse aggregate 1379 divided by 0.5% is the water absorption, that is 1372 kg. And therefore, the total water requirement will be 128 plus extra water for coarse aggregate and fine aggregate. And this is 128. Extra water is difference between these two, that is 6 kg, and difference between these two, that is 7 kg. So water requirement will be 141 kg. Out of this 141 kg, 6 kg will be absorbed by fine aggregate, 7 kg will be absorbed by coarse aggregate, and remaining 128 will be available for the concrete. Super plasticizer will be 4 kg. Now with this, you make the first trial, that is you prepare the beams, measure the slump and adjust the water content and dosage of admixture for achieving the required slump based on trial. The mixed proportion shall be reworked for the actual water content and checked for durability requirement. Cast the beams and determine the flexure strength, and then make 2 more trials having variation in water cement ratio plus minus 10%, and then plot a graph between water cement ratio and flexural strength and get the mixed proportion corresponding to target strength of 5.16 Newton per millimeter square. Check the minimum and maximum content of the cement as per ISA 15, that is 360 to 450 kg per meter cube. So that is how you design a mix. Thank you very much for watching this video. If you have any question, any doubt, you can write in the comment box.